Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. So today we're going to continue our series on work, energy and power, and we're going to attempt a problem that looks really easy at first, but as we'll see, there's quite a lot of detail involved. And I actually spent a lot of time thinking about this concept when I first attempted this problem, and I want to share some of my learnings so that you don't make the same mistakes. Right, so let's get started. A bob of mass m is suspended by a massless string of length L. So we have a bob of mass m and that's suspended by a massless string of length L. The horizontal velocity v at position A, so at the bottom, is sufficient to make it reach the point B. The angle theta at which the speed of the bob is half of that of A satisfies, and we have four options here. And for those of you who are interested in where this problem came from, it's from the 2008 archives. And so let's get started. So what I'd like to do in these vertical circular motion problems is to write down the equations of motion for the bob at a general angle theta. And then we can plug in values of theta like 90 or 180 to understand the motion in very special cases. So what do we know about the bob? What do we know about the forces on the bob at this particular angle theta? Well, there's going to be the force of tension, which is the string pulling on the bob towards the center of the circle. And there's going to be the weight of the bob that acts in the downward direction. All right, and these are the only two forces on the bob. And because the bob is executing circular motion, something must be providing the centripetal force. And in this case, to understand that, we need to resolve the weight into two components, one tangential to the circle and one radial to the circle. So if this is theta, this angle is also going to be theta. And so the weight, the mg vector, can be resolved into an mg cos theta, that's radial, and an mg sine theta, that is tangential to the circle. Right? And the resultant of the tension and mg cos theta must provide the necessary centripetal force for the bob to execute circular motion, which gives us our first equation, that T minus mg cos theta equals m v squared over L. And remember, v was actually, based on the notation used in this problem, v was the speed at point A. So let's use a different notation for the speed at this point. So let's call this point O, a general point O, and so this is speed VO. Okay, V is the speed at point A, and that's given in the problem. So this is one equation. How else can we characterize the motion of this bob? Well, we are also assuming, and that's almost a standard assumption in all problems that we'll encounter, that energy is conserved, right? So there's no friction, there's no air resistance. So the total energy at point A must equal the total energy at point O, which must also equal the total energy at point B. And since we are just concerned about point O, let's conserve energy between points A and O. And another way to conserve energy is to apply the work energy theorem, which tells us that the work done by all forces, so the only two forces are gravity and tension. So the work done by all forces, which in this case is work done by gravity, and the work done by tension, that must equal the change in kinetic energy of the bob, right? What is the work done by tension? Well, it's always going to be zero, right, for circular motion, because tension acts radially while the bob moves tangentially. So they're always perpendicular. So the work done by tension is going to be zero. And what is the work done by gravity? Well, we need to understand the height by which the bob rises to find the work done by gravity. And so again, using some simple trigonometry, let's look at this triangle here. If this is L, this length is going to be, so this length here is going to be L cos theta, right? and the entire length of the string is L, which means the remaining length L here is going to be L times 1 minus cos theta. So that's this length. So L times 1 minus cos theta plus L cos theta equals L, which is the length of the string. So hope that makes sense. So the work done by gravity or the weight of the bob acts in the downward direction while the motion of the bob is in the upward direction. So the work done by gravity must be negative, and it's just the weight times the height by which the bob rises, right? From point A to point O. So minus mgl times 1 minus cos theta. This must equal the change in kinetic energy of the bob. So that's the final kinetic energy, which is half m Vo squared, minus the initial kinetic energy V squared, right? So now we have two equations, right? And as far as I know, these are the only equations you can use in this particular scenario, right? There's a third equation you can use. So for those of you who are really attentive, mg sine theta provides the tangential acceleration, right? This was the radial acceleration, this was conservation of energy, but tangential acceleration is also something that can be, you can write down the equations for it. But for those of you who are familiar, typically we assume the tangential force is only considered for simple harmonic motion, where sine theta can be approximated as theta, and where you can actually solve the differential equation easily. So for large amplitudes of theta, at least at the level that we are dealing with, we don't have the tools to solve the differential equation. So if you're not familiar with that, don't worry about it. But these are the only two equations that we are going to be using for this problem. Okay, perfect. Now, what do we want to understand? So the velocity v at position A is sufficient to make it reach the point B, right? So that means the bob barely reaches point B. It's like when it reaches point B, it's just it's done. So another way of saying that is VO is 0, right? And when is it 0? VO is 0 when theta equals pi. Theta equals pi by 2 is this point, theta equals pi is this point, right? And pi is in radians, of course. And this is the condition that we need to enforce for the bob to reach, for the bob to just barely reach point B, which is the top, right? So what do we get when we substitute these two in equation 1 and 2? Let's substitute this in equation 1. So cos theta, cos pi is minus 1. So T minus mg cos pi, so that's plus mg, equals m v naught squared by L. V naught will be 0 at point B because it's just barely reaching point B. So T plus mg is 0, which means T equals minus mg. Okay, something, I'm not sure where this is going, but let's try applying these to equation 2 as well. Cos theta is, cos pi is minus 1, so minus mgl times 1 minus cos pi, so that's 2, equals half m. V naught squared is 0, so we just have a minus half mv squared, right? So the minus and minus will cancel out, and when we try to solve for v, we actually end up with square root of 4gl, right? And then we could, now that we have v, we can find the theta, right? So v naught would be v by 2, right? The angle theta at which the speed of the bob is half of that of a, and so you could actually find theta, and then we could find which range it lies in, and then we could, that would be the answer. But what I'm concerned by is the fact that the tension that we got at theta equals pi is negative, right? Something is wrong, right? A tension equals 0 is fine because that indicates that the string is slack, but what exactly is going on with the negative tension here? So if you are confused like I am, I encourage you to pause the video here and think about this, a lot more deeply to understand what assumptions we made when we applied equations 1 and 2, and hopefully you can help me solve this problem. Okay, so welcome back. I hope you are done thinking about this. What we need to understand is whether these two equations are valid for all scenarios, because the speed v that we were given here was generic, right? We were not told v in terms of L or M or G or any of the other known quantities. So does the bob complete the circle for any v, right? So are these equations, or in particular equation 1 was written under the assumption that circular motion is being executed, but is that really the case? Well, let's try to understand that. Okay, so let me scroll down a little bit. Okay, we probably have to start. Let me quickly redraw the diagram. Right, so we have the bob that was released from point A. It's released from point A, and now let's actually try it this way, right? We actually got a speed of square root of 4gl, and I'm a bit confused, right? Because this is reasonable, the units are correct, but why does the tension become negative when the bob goes all the way to the top? So I'm just going to use this as a test case and see what happens to the bob when it's given a speed of square root of 4gl at the bottom, right? Let's try to understand that just to get a deeper intuition for this problem. So we'll assume that the bob is released with an initial speed of square root of 4gl, and what exactly happens to the bob? Okay, so to save some time, I'm not going to rederive any equations. I actually want to just use equation 1 and 2 that we I just want to reuse equation 1 and 2 that we got here, right? So equation 1 is from circular motion and equation 2 is from conservation of energy, right? So this time I want to be extra careful. Okay, I want to understand, does the bob actually complete the circle, right? To understand that, see, the equation 2, which is conservation of energy, is always applicable, right? Because I'm assuming, so tension doesn't do any work, because tension is radial while motion is tangential, and gravity, the work done by gravity is always this, independent of, so this doesn't even assume circular motion, right? This is true even if the bob were to move in some weird direction like this. This just depends on the initial and final points. So equation 2 is a lot more, is generally valid, while equation 1 is only true when the bob is executing circular motion only, right? So let me use the equation that's more general, and then we can think about whether equation 1 is valid throughout. Okay, so we're releasing the bob with a speed of square root of 4gl, right? I want to understand, when does equation 1 stop working, right? It's going to stop working whenever circular motion is no longer being executed. And when will that happen? When the tension in the string becomes 0, right? Because as long as the tension is non-zero, it's going to keep pulling the bob to the center. But when this tension becomes 0, at that point the bob is basically in free fall, because gravity is the only force on it. Alright, so to give a different angle to the same approach that we did earlier, let's start off by assuming t equals 0, right? Because this is the more specific case. We want to understand when this is valid, and then we know this is going to be true in general, right? So when t equals 0, we see that substituting t equals 0 in equation 1, we get minus mg cos theta equals m v0 squared by L, correct? So v0 squared is minus gl cos theta, correct? And now let's use this in equation 2, right? So we've basically found the point, or we're trying to find the point at which the tension becomes 0, because we know beyond that circular motion is no longer valid. Okay, so now let's substitute this in equation 2. We also need to remember that V is square root of 4gl, so that can be substituted here. Okay, so substituting V over here and V naught over here, we get minus mgl times 1 minus cos theta equals half m. V naught squared is minus gl cos theta minus V squared, so that's minus 4gl, right? So we have m, the m will cancel, the g and l will also cancel here, right? So we have all of these will cancel. Let me scroll down some more. Okay, the minus sign will also cancel here, so the minus and minus will cancel. So rearranging this a little bit, we get 2 minus 2 cos theta equals cos theta plus 4. Or in other words, 3 cos theta is minus 2. So theta is cos inverse of minus 2 by 3. Okay. Now what does this tell us? So if theta is cos inverse of a negative number, that means theta lies between pi by 2 and pi. Alright. Cos inverse of minus 1 is pi, but this is going to be less than pi. Right. So what this tells us, and this is really the biggest learning that I had when I first thought about this. What this tells us is, let me just make sure I have this over here. Okay. Now what this tells us is that the bob, or the tension in the string, becomes 0 at an angle of cos inverse of minus 2 by 3. So that's going to be somewhere here actually, right? So, and what is the speed at this point? Well, it's V naught squared, which is minus GL. Cos theta is minus 2 by 3. So that's 2GL by 3. So the tension in the string is going to become 0 at an angle of theta, let's call this theta naught, which is cos inverse of minus 2 by 3, whatever that is, somewhere here. But the bob is continuing to have a speed of 2gl. The speed at this point is the square root of 2gl by 3. So the big learning for me when I first did this was, it's actually what we understand from this exercise is that when you provide a speed of square root of 4gl, the bob goes all the way to an angle of cos inverse of minus 2 by 3, and then the tension becomes 0. So it's effectively like the string no longer exists. Okay, and then this bob is actually in free fall, right? So what kind of motion will a bob execute when it's in free fall? And it's a projectile at this point, right? It's actually going to execute parabolic motion, right? It's going to follow a motion that's something like this. And at this point, all along here, the string is going to be slack, right? Because the length of the string is L, but the way the arc that the bob is tracing, the string will not be able to extend to its full length, right? So all over here, even though the string is going to be attached to the bob, it's almost like the string doesn't even exist. So that's what I indicate by a cross. So all through this parabolic arc, the string is going to be slack, and when it reaches this point, which is a distance L away, which is equal to the length of the string, right? At this point, the string is again going to become taut, and when it becomes taut again, there's going to be an impulsive force, so a very high force acting for a short duration on the bob. So there's going to be a very high impulse, and then the motion becomes a bit more complicated, right? We have to make some other assumptions and things like that. So the bottom line is to summarize whatever we just did here, when you provide a speed of square root of 4gl, right, the bob will not actually complete the circular motion. It's going to go somewhere here, and for this particular speed, this was cos inverse of -2/3, and then it's going to follow. Then the string is going to become taut because this quantity is going to become 0 at this point, and then it's going to continue to execute parabolic motion because it's a free fall. The bob is in free fall and it's like a projectile, and then it's going to come all the way here, and when it reaches a point on this circle again, then there's going to be an impulsive force, and then the motion becomes complicated, right? What we did earlier, the blunder that we made when we assumed tension to be 0, or excuse me, when we assumed that the speed to be 0 at the top, is we assumed that the bob would actually get all the way to the top. So we assumed equation 2 was definitely valid, but equation 1 was not true, because as we found out, the bob can slacken somewhere here, and the moment it slackens, it's going to be in free fall, not circular motion, and so equation 1 is no longer valid. Right? So I hope this gives you some intuition on the fine details of vertical circular motion, and we still haven't solved the problem, so I'm going to quickly do that. But I hope the lesson learned here is that it's not we're not guaranteed that the bob will complete the circle for all speeds v. So as you may imagine, let me actually draw this. I think I like to think about it this way. So let's say, or let me use a different color. This is how I like to think about it. Okay, so you have, so basically there's v, which is the speed that is provided to the bob at the bottom, right? That can range from 0 all the way to infinity. And for extremely small initial speeds, it's going to, the bob is essentially just going to oscillate. It's just going to oscillate very close to the mean position. So it's basically going to be in simple harmonic motion. So for extremely small v's, this is going to be in simple harmonic motion. And then we have to find the speed v at which it can get all the way to the top and complete the circle. Right? So that is what we're going to do in the remaining time. And then for any speed higher than that, it is going to complete the circle. So let's actually find out the speed, because we need to plot those points on this line at which the vertical circular motion will be completed. So I realize I am actually out of time, and I don't want to extend the video for too long. But in the next part of this video, where we continue working on this problem, I'm actually going to find out, I actually want to find out different points on this line for which different motions are executed. So there's a certain point, for very small v's, simple harmonic motion will be executed. For slightly larger v's, maybe the bob doesn't even cross theta equals pi/2. Maybe it's just going to execute large oscillations here. Maybe for even larger speeds, it's going to get somewhere here, and then the string is going to slacken and it's going to go all the way to the other side. And then maybe for even higher speeds, it's going to be able to complete the circle. So we still haven't solved this problem, and this is quite an in-depth concept. So in the next part of this video, I will actually work on finding those different speeds and plot those on a line here. So with that, I will see you in the next video. Bye.